good afternoon, and thank you, first and foremost, for this beautiful opportunity to present my research to you today. So my name is Tim Pech. I'm in the last year of my PhD with the Center for Transforming Maintenance Through Data Science. And in today's presentation, I will talk a little bit about extended sequential order statistics, which is a very complicated name, but I'm sure I can try and explain it in very simple terms so that there won't be any issue to follow. Now, I do want to give a little bit of a warning in the sense that these results haven't been applied to any real life data yet. So results are purely theoretical, but I'm sure you'll be able to see how powerful these results are and where they can be readily applied to a bunch of different industry-specific needs. Okay, so to kick off this presentation, I'm just also going to say that it's really separated into two parts. The first one is a little bit technical. We might have to go through a bit of notation and terminology, and then the second one goes into the nitty-gritty of things a bit more, where we are going to take a look at a specific result, a few problems that arise with this result, and how we deal with them. Okay, so kicking off with a little bit of terminology. This research idea is focused on multi-component systems where components are regarded as heterogeneous. And just going to explain a little bit what that means and why this assumption might be reasonable. So there's really two reasons why we might think that components are heterogeneous. The first one is that components are just of different type. So instead of, let's say, considering a system of 4 power generators, for example, which are all of the same type, we might instead be looking at a system where these generators are of different types, so one more powerful than the other one, for instance, or as a specification of that really heterogeneous subgroups of homogeneous components. So I don't know, let's say 2 components of type A and then 2, say, less powerful generators of a different type B. The other reason as to why we might consider components to be heterogeneous is that while they are technically identical, they might have a very different function within a system, and series systems are a very good example of that. So for instance, if we look at 3 wash tanks that filter some inflow, then the first tank receiving the much heavier polluted inflow has to work a lot harder than the second and the third tank respectively. And we might therefore assume or even observe in real life that tank 1 is just more prone to fail than the other 2. So those 2 are reasons or are examples of systems where components are heterogeneous. And that's one assumption, and we're going to combine that with one more assumption, which really goes back to the title of this talk, Sequential Order Statistics, which are a way of allowing us to model a dependent structure between those components. And in particular, what we're trying to model is that the failure of one of these components has an effect on the lifetime expectancy of the other components. So let's say our 4 generators produce a certain power output, and then one of them fails, which is fine because 3 can still generate the power output, but obviously those remaining 3 generators then have to work harder. So what exactly is that effect that our failure has on the other components? And I'm going to explain this in a little more detail with a minimal example. So let's go back to, say, 2 generators and their lifetime distribution being modeled to begin with 2 different distribution functions, might be different color coding. So I'm already embedding our assumption of heterogeneity into this model. And what's really the key point of this slide is that as potentially the first component fails or is taken out of the system for reasons of having to maintain it, the distribution, the underpinning distribution function of the second component is now allowed to be different compared to what it was in the beginning of the experiment. So if we now merge these two assumptions together, we were able to derive a couple of results for a particular data set, that is. And what a data set in this situation is meant to look like is essentially it's going to feature a bunch of failure times. It's what you can kind of regard as our X random variables to represent here. The first failure, second failure, third failure, or even more, depending on the system size, as well as the corresponding failure sources, which is what you can, what the C random variables represent here. So what was the first component to fail, which was the second, which was the third, and so on. The data set is essentially, or consists of a bunch of times that we have observed these failure times for a particular system or for a bunch of independent systems of the same structure. And ultimately, we are able to use this data set to derive so-called MLEs, maximum likelihood estimates. And I'm going to demonstrate this using the exponential distribution as underlying distribution functions here. But really the result can be achieved for any distribution function. It might just not be able to analytically, to get an analytically representation. So results might have to be derived numerically instead. And as I said, the first exciting result is that we were able to derive maximum likelihood estimates, which for the underpinning model parameters, in case of an exponential distribution, that would be the essentially the rate of failure, or we could also call it the risk of failure, which governs the entire structure of the distribution. And therefore, once we've got a better understanding of this parameter, we also know quite well how components behave individually and at each stage of the experiment, as well as obviously the entire system behaves. Okay, so just to finish off with this first part, introducing a little bit of tricky notation that I do have to emphasize because it's going to be important for the second part. So going back to our exponential distributions, on the first level, in this minimal example, we would consider the first component to follow an exponential distribution with parameter lambda1, the second with lambda2, and then on the second level, we then have to introduce a novel distribution function for that potential change in behavior. We're going to use a notation here, which is lambda and then 2 given 1. So that represents the risk of failure for the second component, given that the first component has already failed. Okay, so now we're going to go into the second part of this presentation, where I'm going to, first of all, demonstrate the power of these MLEs. I'm just going to, before I start to actually point out the results, I'm just going to run you through the idea, what's going to follow, which is that for a particular choice of parameters, we are able to generate data just by simulation, then apply our formula for the MLEs, calculate those MLEs, and see if we are able to recover the true parameters. And I'm going to demonstrate that with this particular system here. So 3 wash tanks. Going to make an arbitrary choice for the model parameters with the assumption that we discussed earlier, which was that tank 1 should really be the most prone to fail, then tank 2, then tank 3. So I'm going to assign 3, 2, and 1 as a risk of failure rate to the tanks 1, 2, and 3. Now, because or in a setting of sequential order statistics, what's going to happen in a second level, for instance, because while ideally the inflow should be really filtered through all the 3 tanks, but say it's also possible that only 2 or potentially even 1 tank is okay. we therefore are able to go in and fix one of the tanks and only have 2 of them actually being operational. So essentially bypassing a tank. We then have to introduce novel distribution functions. To begin with, 2 for each, so a total of 6, 2 for each component. For instance, for tank 1, we need 2 additional distribution functions, one which represents the lifetime of tank 1 given that tank 2 has already failed, and 1 given that tank 3 has already failed. Now, saying that, by this particular design of this problem, we don't actually have to introduce any new distribution function for the first tank, because the first tank is not affected by a failure of the second or the third tank. However, the second tank would be affected by a failure of the first tank, because then we have to bypass tank 1, send the heavily polluted inflow straight into tank 2, and therefore that tank really takes the role of tank 1, and therefore we just assign the same risk of failure on the second level to tank 1 than we did on level 1 to tank 1. Okay, and a similar idea for the third tank. This is all getting very complicated. The essence here is we try to make a reasonable choice, arbitrary but reasonable choice for our model parameters, and now we're just going to simulate data. And we do that 10, 25, 50, or 100 times. So quite different sample sizes. And if you take a look at the last 2 rows of this table, now in the very last row, I've just restated the true parameters. But then in the second last row, so if we have a quite large sample size, we can see that our MLEs are quite close to the true parameter value, which is good. That's an exciting result. So yes, we were able to recover the true values, which essentially tells us, okay, those MLEs give us a reliable estimate for our model parameters. However, and some of you might have already noticed this, there's also a little bit of an issue going on, actually a few issues, particularly when sample sizes are small. So I've highlighted 2 examples here. The first one I called incorrect sensitivity rating between components. So if you take a look at these blue circled estimates, so the risk of failure for the first and the second component, then what this data seems to suggest is that the first component is less prone to fail than the second, which might not be what our engineers have been telling us for the past decades. And we're a bit puzzled as to why this might have happened. Now we have two choices. Either we just throw our hands up and are like, oh, we don't know what this means, and we don't have any results really. And the other one would be to just accept that seems to be the case, although our experts might disagree. A different problem, potentially even worse, is that there doesn't even exist an estimate. And I've put a 0 into this table, but really it should say no estimate available. Because what happened in this particular case is that the third tank was just never observed to fail first. So it's something that statisticians are usually aware of when working with small samples, which is that it becomes difficult to estimate anything if we don't observe something. And in both of these cases, there isn't a whole lot, unfortunately, that we can do about it. So I'm going to point out a different issue, and then I'll talk a little bit about the solution for this one. And that is called incorrect sensitivity rating between levels. So again, take a look at these 2 estimates, which are circled in red here. So lambda2 and lambda2 given 1. Now these estimates are suggesting that the second tank starts to perform better once the first one has failed, which might not make any sense, and again is completely against what our engineers have been telling us for the last years. So in this case, we are proposing a solution which essentially features the idea to just force an order restriction onto our parameters, because in essence, we would like the risk of failure for any component really to only increase as a result of other components having failed. So the order restriction that we are trying to impose here is, in particular for the second component, let's say that lambda2 has to be not greater than lambda2 given 1. And the corresponding so-called order restricted MLEs turn out to coincide with the solution of the isotonic regression over the unrestricted estimate. And that sounds very complicated, but once again, can probably explain this in simple terms. So let's go back to our example. These estimates are ordered basically incorrectly. They violate our order restriction. And the new solution is simply a weighted average of these two values. Now it's not, okay, I'm going to go a little bit into detail with that. Why is it weighted and why is it not just the average? That's because the number of observations that we have available, or that played a role, I'm going to say, in the estimation for both of these parameters varies. So, for instance, lambda2 was estimated based on 10 observations. And that's because regardless of the second component failed first or didn't fail first, there's always a piece of information available. In the first case, we essentially know the component lived up to a certain point in time. And in the second case, we know it survived that point in time. Now that's different once we look on the subsequent, once we try and perform estimation on the subsequent levels, because if, let's say, component 2 has failed on level 1, then we don't really have any information about component 2 on the next level. And that's exactly what happened here. In 4 instances out of our 10 trials, component 2 failed first. And for that reason, the estimation process of the level 2 parameter was performed based on 6 observations. So that's where these weights come from. And that's how we then basically derive the new MLEs, which adhere to that order restriction. Okay, and I'm just gonna maybe go a little bit deeper into that using a graph in which you find that original estimate. I'm just gonna go back to those numbers, 2.68 and 1.83. In this case, represented by this red dot. So you can see on the x-axis, we have our level 1 parameter, on the y-axis, the level 2 parameter, and the red dot is where 2.68 and 1.83 intersect. And the same thing that we did to derive this pair of unrestricted MLEs was essentially repeated 100 times. So in this graph, you have 100 circles, each representing a pair of unrestricted MLEs. And sometimes these are perfectly fine in terms of our expectation, and sometimes they will violate, just in that example that we went through, that expectation. And those two cases are essentially separated by this dotted line. Okay, so what we just proposed in this case is to calculate the order restricted MLEs instead. And if we do that, then what we will notice firstly is that every time the unrestricted MLEs adhere to the order restriction, they will just coincide with the order restricted MLEs. And every time they don't, the corresponding order restricted MLEs are simply a orthogonal projection onto that dotted line. Now that's obviously very easy to understand in a 2D setting. It gets more complicated and impossible to visualize for greater dimension, but the idea is exactly the same. We will always have an orthogonal projection onto the cone that is essentially defined by our order restriction. Okay, so we now have a solution which essentially says just use the order restricted MLEs. They will perform better or as well as the unrestricted ones. And that gives us a solution to that problem, which I outlined beforehand, where especially for small sample sizes, the order of parameters that we estimated might just not give us a reasonable solution. So we can overcome that with this newly proposed idea. Regarding where this research idea is headed next, first and foremost, as I said before, we haven't applied this to any real-life data yet. So I still hope that one day we'll be able to get some industry data and showcase the power of this model. And then there's two more ideas. The first one is to introduce, well, actually there's more than that, but two ideas which kind of head the same way. The first one is to introduce an equal load assumption to the model. And we have a little bit, or actually we've seen an example of that with the wash tanks. The idea is that it doesn't matter which component exactly failed, but only that a component failed. So we basically just separate between levels, not depending on which exact component has failed. So to go back to our exponential example and the notation that we have used, remember how I said on the second level, for every component, we need 2 additional distributions, which means 2 additional parameters. Now with that assumption, that would reduce down to 1. So you're, for instance, for the third component, you'd be saying that we need a parameter that describes the risk of failure on the second level for the third component, but doesn't separate between whether it was the first or the second component that failed on the first level. And the result of that is that we get a very large reduction in the size of the parameter space. Now, in this example, that doesn't seem to be like all that much, but let me tell you that the number of parameters needed in this model increases exponentially with the size of the system. So it just explodes, even for like smaller systems. And for this reason, this assumption is very powerful, because in comparison to that, we now only need n, where n is the size of the system. So let's say you have 5 components, then you only need 5 parameters on each level, and that we can handle. Headed into the same direction is another extension to the model that we could think of, which is the introduction of link functions. So for these parameters, say for the third component, lambda 3,1, then for the first level, lambda 3,2 for the second level, and so on. There might be an underpinning relation between these, whether that's just a regression equation, or one might also consider log-link functions, where again the number of parameters could be reduced, and therefore the applicability of this model could be increased. So both of these ideas are really heading towards making this model more readily applicable, because the number of parameters is being reduced. So that's for the future. For now, I'm gonna conclude my talk. I'd like to thank you for the opportunity once again, and if you have any questions, feel free to ask now if you've got the time, or also reach out afterwards if you like. Thank you.